Good afternoon. We are going to start on lecture number 4 of electric drives course now. We had already looked at various aspects of electric drives, such as, first of all, we looked at the overall configuration of an electric drive system. We also looked at what all different kinds of loads are generally expected in a drive system, and we looked at the dynamics of the load system, which is connected ultimately to the motor itself, coupled to the motor itself through either gear arrangement or through translational to rotational conversion mechanism. So now let me just start sharing my screen. And so in the last class, I mentioned that you would normally see in an electric drive system sometimes gear arrangement, sometimes the arrangement which converts translational to rotational motion. And at that time, we talked about two things. One is conversion of the load torque in such a manner that what is the equivalent torque that is visualized from motor shaft. This is one thing we talked about repeatedly. The second thing that we talked about was moment of inertia, rotational moment of inertia that is visualized from the motor shaft side. So these are the two things we talked about. So please note that moment of inertia plays a very, very big role, especially when we talk about the dynamics of the drive system itself. We already wrote the equation, mechanical equation of the drive system, saying that J d omega m divided by dt, that is going to be equal to TE minus TL, where this d omega m by dt is the angular acceleration of the drive system. And we said that TE is going to be the electromagnetic torque, and we have TL to be the load torque, and J is the moment of inertia of the drive system. So drive and load system put together, in fact. So if I want a particular amount of acceleration with the given inertia of the drive system, I will have to give an electromagnetic torque which is greater than TL, which is actually greater than the torque demanded by the load itself. For example, if the load torque is something like 3 Newton meter, if I generate an electromagnetic torque of, let us say, 5 Newton meter. So what is there in excess as compared to the load torque is only 2 Newton meter. So TE minus TL is going to be 2 Newton meter. And this is the only excess torque available for accelerating the drive system. So this also can be specified as accelerating torque. So the accelerating torque will go towards increasing the velocity, increasing the speed of the system. So that is going to be governed. How much speed increase is happening, that is governed by what is J. Whatever is the J value, that is going to decide how much is the acceleration that is imparted to the entire drive system. So if there is a higher inertia for the entire configuration, the rate of rise of speed is going to be pretty slow. We are not going to have quick acceleration in the system. If the inertia, on the other hand, if it is small, then even a little bit of excess torque can really impart a huge amount of acceleration to the system. This is one reason why, in the case of electric vehicles, the vehicle itself is heavy. So we are going to have J to be very, very high. Because J is high, unless we give a good amount of electromagnetic torque, we are not going to be able to accelerate the drive quite quickly. So that is the reason why generally starting torque requirement for electric vehicles, that is really, really high. It is going to be really high. So the inertia plays a very, very huge role in deciding how quickly your drive system would respond. If you look at different electrical machines like induction motor, three-phase induction motor, then three-phase synchronous motor, and DC motor. Any of the DC motors, any of them will normally have commutator arrangement which is attached to the rotor. So in general, inertia of the DC motor is going to be the highest if I look at all these three motors simultaneously. Three-phase synchronous motor will be somewhere in the middle. And three-phase induction motor, especially if I am talking about screw cage induction motor, because you don't have any connection out of the rotor system and all you have is a cage arrangement. So generally the squirrel cage induction machine is going to have the lowest weight or lowest inertia. So this is going to have the lowest inertia. And in general, induction motor is characterized by it is high torque to weight ratio or power to weight ratio. So for a given power rating, if I compare the sizes of three-phase induction motor, three-phase synchronous motor, and DC motor, we would see that the three-phase induction motor happens to be the smallest and the DC motor happens to be the biggest. So you are going to see that generally the induction motor is preferred in many of the applications because of its small size and it has a very high torque to weight ratio, which means the kinetic energy stored in an induction motor is going to be very small as compared to a DC motor. And that also explains why three-phase induction motor can accelerate or pick up speed much faster than any other motor. So in general, if we have the dimensions of the machine, we should be able to calculate what is the kind of volume it occupies, and depending upon the kind of material we are using for making the machine, we should be able to calculate its weight. And if I know the weight, I should be able to calculate the moment of inertia as well. But in most of the cases, we may not have all the dimensions of the machine available. If it is not available, we are not going to be able to calculate the moment of inertia very easily. That is the reason why we should know how to determine the moment of inertia. So determination of moment of inertia of an electric drive system. That's what we are going to discuss. So to determine the moment of inertia, what we conduct is a test called retardation test. So in a retardation test, what we do is run the machine at a speed which is greater than the normal rated speed. So you are going to run it, for example, if 1500 RPM is the synchronous speed of a squirrel cage induction machine, and the nominal speed is 1470 or 1460 RPM. This is going to be the omega rated. Then what you would do is run the machine at a speed greater than 1460 RPM if it is possible to do so. So you may run it at 1500 RPM. So when you run a three-phase induction motor, if I assume that this is the stator winding of the three-phase induction motor, and I'm going to show the squirrel cage somewhat like this. This is the cage. So this is the representation of the rotor cage. So this is the cage. Now this three-phase terminals are connected to the three-phase supply, maybe through a switch. So I'm going to connect it through a switch to the three-phase supply. So this is A, this is B, and this is C, which is three-phase supply. So once the machine picks up speed and runs close to 1500 RPM, all I'm going to do is to open the switch. Now, after it attains steady state speed, you open the switch. Then what we do is we note down what is the speed of the machine with respect to time. So let us say at 0 second, we are going to have 1500 RPM. So we are going to see what happens at 0.1 second, 0.2 second, 0.3 second, and so on until it stops completely. Maybe it stops at 0.8 second or 1 second. So you are going to see that the speed comes down, pretty quickly, and then it might reach almost zero speed at the end of 0.8 second. So this is the kind of reading that we need to note down. And this particular test is known as retardation test because you are allowing the speed to slowly decrease. Now, if you have this, you should be able to plot a graph where you would say what is the time and what is the speed. So at 0, it is 1500 RPM and then it is decreasing. Maybe it is not decreasing linearly, it will decrease non-linearly. So we can plot the curve somewhat like this. It may come down, slowly. So this is the speed versus time plot. Now, if I want exactly what is the kind of slope I am having at 1470 RPM or 1460 RPM, I should be able to draw a tangent here. So I can draw a tangent to this particular graph like this. And then I should be able to calculate what is the kind of slope this particular tangent is having. That will give me what is d omega by dt or d omega m by dt at rated speed. So once I have this d omega m by dt, I should be able to say generally the energy that is stored in this rotational system that is going to be half j omega m square. Okay. Now, if I try to say d by dt of this energy at a particular omega, which is omega rated or something, I should be able to write this as j omega m rated multiplied by d omega m divided by dt, which is again at omega rated. So this rate of change of energy is actually the power that is being consumed by the motor when it was running at omega m, at a speed of omega m. So only hitch here is, if you really note down the power reading, the wattmeter reading at this particular juncture when it is running at rated speed, you are going to see that this consists of two components. One is whatever is the rotational loss that is incurred by the machine. The other one is going to be the core losses incurred by the machine. So you will have, even under no load condition, you will have two components of losses. One is going to be rotational loss, which is actually the mechanical loss of the machine, which we are interested in because what we are actually getting is a mechanical quantity, which is moment of inertia. Then there are going to be core losses. But it's very difficult to segregate these two, assuming that the core loss is really, really small. we can attribute this entire thing to the rotational loss. So we are going to say this is P, whatever is the wattmeter reading that you have noted down under no load condition. This is going to be P. So we already have d omega m by dt from this retardation curve. We know what is omega m and we have the wattmeter reading P, from which we should be able to calculate what is moment of inertia. So I should say J is equal to P divided by omega rated divided by d omega by dt at omega rate. So this should be able to give us what is the moment of inertia of this drive system. But of course, there is an approximation because we are actually assuming that the entire losses what you have measured is rotational loss and there are no core losses. If you really want to do this accurately, then one way of doing it is, if it is a DC machine, you should keep the field system still on. So excitation should be on. And if you have the excitation on, what you get as the losses, what is your loss here, that will consist of rotational losses plus armature losses. So armature losses will be IA square RA. It is quite easy to compute IA square RA because most of the times we will know what is the armature resistance and we can measure what is the armature current. So this can be definitely computed, which means P minus IA square RA will automatically give me rotational loss, and I can use this rotational loss is equal to J omega d omega by dt, from which I should be able to get what is the value of J. And if it is a synchronous machine, if we are talking about a synchronous machine, so in the case of a synchronous machine, we should be able to again keep the excitation on. So excitation can be on in this case also, so that the core losses are taken care of there. The same kind of calculation will hold good for synchronous machine as well. Of course, it must be three-phase. So you have to calculate 3 IA square RE. So that should also be able to give you what is the moment of inertia quite accurately. If we are talking about wound rotor induction machine, if we are talking about wound rotor induction machine, so wound rotor induction machine basically will have windings in both stator as well as rotor. Whereas in squirrel cage induction machine, the rotor is going to just have rotor bars. So you are going to have two end rings which are short circuiting the rotor bars which are sitting here. So these are the rotor bars which are actually carrying the rotor current. So this is going to be the kind of structure you are going to have in the case of a squirrel cage induction machine. So this is end ring. What I have here is end ring. And these are going to be rotor bars. So they are short circuited already with the help of end ring. So you would not be able to disconnect or measure the current, or you cannot just interfere with the working of the rotor itself in the case of a squirrel cage induction motor. Whereas in a wound rotor induction motor, both stator and rotor are going to have windings. If I say this is the stator winding, the rotor winding is also a three-phase winding, and those terminals are going to be brought out and they may be externally short-circuited. So in wound rotor induction machine, again, we can have the excitation on the stator side. Stator side excitation can be on, whereas rotor side can be opened out. So if the rotor side is opened out, automatically it is going to stop. So you can do the retardation test by opening out the rotor connection, and you can allow the excitation to continue from the stator side so that you have core losses taken care of. So you can actually minimize the error in at least these three kinds of machine, but it is going to be very difficult for us to minimize the error in the case of cage rotor. It is going to be very difficult to minimize the error. So approximately what you get as the moment of inertia J will be the power wattmeter reading what you get divided by omega m divided by d omega by dt, which you obtain from the retardation test. There is another way through which you should be able to calculate the moment of inertia. So let me try to tell this. This is method 2. What we got here is method 1. This is method 1, where you try to get directly the moment of inertia as P divided by omega divided by d omega by dt. So in this particular case, in method 2, what we are looking at is we try to run the machine at different values of speed. So run the machine at different speeds, for which you might have to use a variable frequency supply and get corresponding rotational loss or P reading. So you are going to get the power loss reading at different values of speed. And the second thing you are going to do is to conduct retardation test. So retardation test you are going to conduct. Now, after conducting the retardation test and plotting what is the speed versus time. So you are going to plot what is speed versus time. Let us say it is somewhat like this. It's going to start from a particular value and then come down like this. So this is speed versus time. And you have got already at different speeds what is the power reading or the loss. So that also you are going to plot. So this is going to be speed, and you are going to plot what are the losses with respect to speed. So maybe it will be a certain value like this, and then it is going to increase like this. Maybe it will saturate at a particular value. So this is the kind of reading you are getting for power versus speed. Now, when you combine these two plots, we are going to combine these two plots and say at different time interval, what is the kind of power loss the machine could have incurred depending upon what is the speed. So you have, let us say, this is corresponding to 1400 RPM. And this corresponds to probably 0.2 second. And here, if you look at it, maybe corresponding to 1400 RPM, I am having a power loss, which is probably 800 watts. I'm just taking arbitrarily some value. So like this, for every other speed, I should be able to get what is the power loss, and I should be able to plot what is the power loss with respect to time. So if I plot power loss with respect to time, maybe when the speed is high, the power loss would also have been high and it would slowly come down to zero. So this is going to be the kind of plot I'm getting for power loss versus time. In which case, if I try to look at the area under this curve, if I try to get the area under this curve, so this is as good as integrating P, the power loss with respect to time. So this should be the total energy lost during the entire interval of time. So this energy loss should be equal to half J omega m square, where omega m is probably the starting speed from which I had, like retardation test, at the beginning of the retardation test, what was my mechanical speed for this machine? So this is half J omega square. And this is essentially the area under this curve. If I say this is A, so this is A, which is the area under P curve. So from this, we should be able to get what is J, because we know what is omega m. We have already calculated what is A. So J can be inferred from this as well. So these are two methods which can be used really to calculate what is the moment of inertia experimentally from a drive system. But in either case, it is very important to conduct retardation test. Without retardation test, it will not be able to work. Okay. So retardation test is a very, very important test that needs to be conducted for getting the moment of inertia. Okay. Now, if we are having the moment of inertia and we know really at what rate my drive system is accelerating, I should be able to calculate how much time taken for attaining a specific speed. This I should be able to calculate if I know the moment of inertia and so on. And another thing is, I should also be able to calculate how much is the energy loss during acceleration or retardation or something like that. So how much the energy loss is, this also we should be able to calculate. So how do we really go about calculating the time taken for acceleration? We normally write half j omega square is the energy stored in the rotational system. And if I am looking at the mechanical equation, which says J d omega by dt equal to Te minus TL, I should be able to write this as dt equal to J d omega divided by Te minus TL. Now, both Te and TL could be functions of speed, or TL could be a constant and Te could be a function of speed. So if I write this equation as this is equal to J multiplied by d omega m divided by Te of omega m minus TL of omega m. If these are simple functions of omega which are integrable, then it is much simpler, in which case we should be able to calculate the time required as integral of this itself. So I should be able to write this as, if I want to accelerate the drive from 0 to certain omega m, then I should be able to calculate how much is the time. But even if it is a first order term, what I'm having here is a first order term. Even if the load torque is proportional to speed, or if the electromagnetic torque developed by the motor is proportional to speed, if I try to integrate this, I will see that to reach a particular value of omega m, the m1, it is going to take infinitely longer time, because it will have an exponential term which will have e power minus t by tau, where tau will involve this omega and j and so on. So it is going to definitely take infinite amount of time if I try to look at omega m1 as being the only speed that is acceptable. Rather than that, if I say omega m is 95% of omega m1, if I attain, that is sufficient enough, or 90% of omega m1 if I attain, that is sufficient enough, then we will get a finite duration. So if we allow a small margin between the actual reference speed that I'm anticipating the drive to achieve, and if I give a small margin, in that case, I'll get a finite time duration. So the time can be calculated quite easily by integrating this d omega divided by Te minus TL. If I try to integrate it with respect to the speed, I should be able to get exactly what is the time duration that is required for accelerating the drive from zero speed until a particular speed, what I am expecting the drive to attain. When I am looking at the machine accelerating slowly, it is actually developing a torque which is corresponding to Te. Because it is generating a torque, obviously it is going to carry a current. So if it is carrying a current, I square multiplied by R. If it is a DC machine, I have to take RA. If it is again synchronous machine, I can again take RA, which is the armature resistance, but I have to multiply this by 3 for getting three-phase armature losses. And if it is induction machine, again, I have to take I stator, but I should take the resistance which is involved in the rotor winding as well as stator winding, and I should multiply that by 3 as well. Because for all the three phases, I have to take into account what are the copper losses that are incurred by stator as well as rotor. So I have to take this I square RA, and I have to take this from 0 to whatever is the time duration that is needed for acceleration. And I have to multiply this by dt. If we are going to have the resistance itself as a variable, which is going to depend upon the temperature or depending upon how much is the current carried, if the resistance is going to change, then I cannot take this as a constant factor. Now, this entire thing is going to give me what is the total energy loss incurred by my drive system when it is accelerating from zero speed until omega n. So I am definitely going to have the calculation of energy loss done, provided I have the current available with me, and I also have the resistance of the winding which is carrying the current that is available with me. Then I should be able to calculate the energy loss. Okay. Now, having looked at these three factors, the first thing what we had seen was a system with gear and rotation to translational converter. The second thing what we looked at was types of load torque. These two we had seen in the last class itself. The third thing what we took a look, that was actually having the determination of moment of inertia by retardation test. And the fourth thing what we just now saw was time taken for acceleration and energy lost during transients. So these are the 4 points that were discussed so far. These are the 4 points these were discussed so far. So now what we are going to do is to work out a few problems based on these concepts what we discussed, so that we really know how to apply these concepts that we studied so far. Then after that, we'll proceed further. Okay. So let me first take problem number 1. This is based on rotational to translational converter. So the problem statement goes as follows. A weight of 500 kg is being lifted by a hoist at a speed of 1.5 meters per second. This is driven by a motor rotating at 1000 RPM. Moment of inertia of the motor and drive mechanism are 0.5 and 0.3 kg meter square respectively. Okay. Calculate the equivalent torque T equivalent and J equivalent as seen from the motor shaft if the motor has to develop a torque of 100 Newton meter in the absence of weight to keep the mechanism rotating or keep the motor shaft rotating at 1000 RPM. Okay, so let us try to see how to solve this problem. So first of all, this is a hoist mechanism. So we have to assume that it is very similar to your elevator or lift mechanism. So probably you are going to have a weight that is being lifted up like this, and you may have a counterweight or something like that on the other side. And you are going to have this rotating in this direction if the weight is moving up. And to this shaft of the motor, you are going to have this shaft, you are going to attach the motor. So the motor is going to impart power by rotating this middle shaft, and through which this pulley is going to rotate, and that is going to cause the movement of this weight up and down. So this is going to go up or down depending upon whether the pulley is rotating in clockwise direction or anti-clockwise direction. This is the kind of mechanism you're going to see. So what is given is the weight is 500 kg. The weight here is 500 kg. And that is going against the acceleration due to gravity. So if I have to really calculate the force exerted by this weight, which will be pulled down, that is essentially the force is essentially due to gravity. So the force exerted by the external weight, that will be mg. So m is 500 kg. G is acceleration due to gravity. So I should say this is what is 9.8. So this is meter second power minus 2, and this is going to be kg. So what I get is the force in newtons. So this is going to be 500 multiplied by 9.8. That will be 4,900 newtons. That is the force exerted by the external weight. And this is F. And we said that F multiplied by V is the power. The power requirement of this load, that is going to be F times V. So this will be 4,900 multiplied by 1.5. Because 1.5 is the speed at which this particular weight is being lifted. So this is 1.5. So 4,900 multiplied by 1.5, that is 7,350 watts. So this is the power that is required by the load when it is to be lifted. Now, we said that the motor is rotating at a speed of 1000 rpm. Because it is rotating at a speed of 1000 rpm, we can calculate radians per second because we ultimately require the power, and power is going to be T multiplied by omega. So this omega should be in radians per second. So I'm going to calculate what is the radians per second here. So that is going to be 2 pi n divided by 60. So 2 pi n is the speed in RPM, that is going to be 1000 divided by 60. This will give me radians per second. So that will come out to be 104.7 radians per second. So this is the rotational speed. Okay. Now that we have this as the rotational speed of the motor, if a power of 7,350 watts need to be developed by this motor rotating at 104.7 radians per second, the torque has to be the TE, that is electromagnetic torque, to be developed. That is going to be equal to 7,350 divided by 104.7 radians per second. So that is going to be the torque that needs to be developed by the motor. That comes out to be approximately 70.2 Newton meter. And it is already given if the motor has to rotate even in the absence of the weight, if it has to rotate at 1000 RPM, the torque to be developed is 100 Newton meter by the mechanism. So which means the total torque to be developed by the motor will be 100 plus 70.2, which is 170.2 Newton meter. 170.2 Newton meter needs to be developed by the motor. if it has to lift a weight of 500 kg at a speed of 1.5 meters per second. So this is the equivalent load torque that is visualized by the motor shaft, or it has to develop, the motor has to develop 170.2 Newton meter if such a mechanism has to work successfully. The next one that we need to calculate is the moment of inertia. So moment of inertia calculation. So the first thing we need to calculate is, by the translationally moving mechanism, what is the kinetic energy stored? So at 1.5 meter per second of velocity, 500 kg weight will store a kinetic energy of half mv square. So that is going to be half multiplied by 500 multiplied by 1.5 square joules. This is what it is going to store. Now, if I have to look at it from the motor point of view, I have to equate this to half J equivalent multiplied by omega m square, where omega m is the rotational speed of the motor. So that will be half J equivalent multiplied by 104.7 whole square. So from this, I should be able to say J equivalent should be equal to 500 multiplied by 1.5 square divided by 104.7 whole square. So this is the J equivalent or equivalent moment of inertia posed by this 500 kg load when it is moving at 1.5 meter per second when you visualize it from the motor shaft. So this comes out to be 0.1026 kg meter square. Okay, in which case we can say the total value of J, that is moment of inertia. It is already given that the motor and this other mechanism, each of them have the moment of inertia corresponding to 0.5 and 0.3 kg meter square. So I have to add all of them, which is 0.5 plus 0.3 plus 0.1026. This is the total moment of inertia of the entire system when it is visualized from the motor shaft. So this comes out to be 0.9026 kg meter square. Okay, so I have just worked out one problem to understand how the conversion of moment of inertia and conversion of torque is done with reference to motor shaft. But nevertheless, there are more number of problems that are available as exercise problems in G.K. Dubey's book as well as in N.K. Day and P.K. Sain's book, even S.K. Pillai's book. So you might like to look at them so that you get used to working out more problems and understand the concept more thoroughly. Okay. Now we are going to look at one more problem regarding calculating time taken and energy lost during transients. So we are going to look at this through another worked example. So the problem statement goes as follows. Calculate the starting time requirement of the drive whose TE, electromagnetic torque, is given by the equation 15 plus 0.5 omega m, and load torque is given by the equation 5 plus 0.6 omega m, and moment of inertia of the entire system is given by 10 kg meter square. So first of all, what we need to calculate is the time needed for accelerating to the steady state speed. So before everything, we need to calculate the steady state speed. So equilibrium will be achieved when TE equal to TL. So I should write first of all 15 plus 0.5 omega m is equal to 5 plus 0.6 omega m, which actually tells me that 15 minus 5, which is 10, equal to 0.6 minus 0.5, which is 0.1 omega m. So from here, I should say omega m is equal to 100 radians per second. So under steady state condition, this particular mechanism is going to maintain a speed of 100 radians per second, which actually makes TE equal to TL. This is going to be the final steady state speed that is achieved by this mechanism. Okay. So now to calculate the time taken for accelerating to 100 radians per second, I can write the equation J d omega by dt equal to TE minus TL. So first of all, I'm going to write this TE minus TL. TE minus TL happens to be 10 minus 0.1 omega m. I'm just substituting these values here. So TE minus TL comes up to be 10 minus 0.1 omega m. So I should say J happens to be 10 multiplied by d omega. So d omega m divided by 10 minus 0.1 omega m is equal to dt. So if I want to achieve 100 radians per second completely, to achieve this steady state, if you actually calculate the time, it will come out to be infinite amount of time. So I'm going to take this as 95% of this speed is assumed to be steady state speed. Or if 95% of the speed is achieved, I'm going to say the system has already reached steady state. So this is going to be the steady state speed. So I can write this as integral dt to achieve complete steady state is equal to 10 d omega m divided by 10 minus 0.1 omega 0.1 omega m, 10 minus 0.1 omega m, and this has to be integrated from 0 radians per second until 95%, which is 95 radians per second. So I can say d omega m divided by 10 minus 0.1 Wm. That is essentially going to be natural log of the integral value will be ln. So I should be able to write this as 10 divided by 0.1, right? So which will come out to be 100 multiplied by log base e of 10 minus 0.1 omega m. Okay. And the limits what I have to substitute are from 0 until 95 radians per second. So when you calculate this value, this comes out to be 299.5 seconds. So this comes out to be 299.5 seconds, which means it takes almost 300 seconds for this system to reach the steady state speed. To reach the steady state speed, this particular system takes almost 300 seconds. So this is a typical calculation of time taken for accelerating a particular drive system from zero speed until steady state speed. But rather than assuming the steady state speed to be 100% value, we can take approximately 90 or 95% value, which is almost getting there, so that you get a finite value as the answer rather than getting infinite amount of time. So in the next class, in the next lecture hour, we are going to look at plan for the next class. So we are going to look at one is what is meant by the load characteristics of some of the practically existing systems. So practically existing systems. For example, if we consider a fan, if we consider a high-speed elevator, if we consider a train, how are we going to have the speed torque characteristics? That we are going to take a look. Then we are going to talk about something called steady state stability. Then we will also be talking about load equalization. That is, if I am going to have a load which is going to be extremely large for certain duration of time, and it is going to be literally zero for certain duration of time. Again, it is going to be very large for certain duration of time, then it is going to be zero for certain duration of time. How will we make the system feel as though the load is not varying so much? Will we be able to somewhat put something like a filter which will reduce the variation in the load torque visualized by the motor? So this is generally known as load equalization, and we would be looking at that as well in the next class.